You have 90 seconds of consciousness left. Your helmet just cracked. Your blood begins to boil. Your lungs collapse. You're freezing and suffocating simultaneously. This is Mars. This is what awaits us 225 million kilometers from home, and we're planning to send people there permanently. The question isn't whether we can get to Mars, it's whether humans can actually survive there. And here is a question. If you could change one thing about Mars to make it habitable, what would you choose first? Comment down below. I'll pin the most creative answer. Now let's begin. We need to start with something fundamental, something that separates Mars from Earth in ways most people don't fully grasp. When scientists at NASA, the European Space Agency, and private companies like SpaceX run their calculations, they focus on engineering challenges. How do we get there? How do we land? How do we produce fuel? These are important questions, but they miss the bigger picture. The real issue isn't whether we can visit Mars. We absolutely can, and we probably will within the next decade or two. The question is whether human beings, as biological organisms shaped by 3.8 billion years of evolution on Earth, can actually survive and thrive there for extended periods. Can we build families? Can we raise children? Can we create a civilization that doesn't depend on constant supply shipments from our home planet? The scientific evidence accumulated over decades of Mars exploration suggests the answer is deeply troubling. Let me paint you a picture of what Mars actually is. Not the romantic version from science fiction movies, but the real Mars revealed by missions like Curiosity, Perseverance, InSight, and the Mars Reconnaissance Orbiter. It's a world that's simultaneously familiar and utterly alien. Mars is roughly half the diameter of Earth, which means its surface area is about equal to all of Earth's land masses combined. That sounds promising until you realize what that surface is actually like. The average temperature on Mars hovers around -80 degrees Fahrenheit. That's -62 Celsius for those keeping track. During the warmest summer days at the equator, temperatures might climb to a balmy 59 degrees Fahrenheit, about 15 Celsius, but at night, even at the equator, they plummet to -100 degrees Fahrenheit, -73 Celsius. These aren't just uncomfortable temperatures, they're lethal. Human skin exposed to these conditions would suffer frostbite in minutes. Your lungs would freeze from the inside if you tried to breathe. But temperature is just the beginning of our problems. The atmosphere of Mars is so thin it barely deserves the name. Earth's atmospheric pressure at sea level is about 1,013 millibars, or 14.7 pounds per square inch. Mars, 6.1 millibars on average. That's less than 1% of Earth's pressure. To put that in perspective, the air pressure on Mars is equivalent to being about 100,000 feet up in Earth's atmosphere, well above the Armstrong limit. That's the altitude where water boils at human body temperature. What does this mean practically? If you stepped onto the surface of Mars without a pressure suit, the liquids in your body, your blood, your saliva, your tears would begin to boil. Not because it's hot, but because the pressure is so low. You'd lose consciousness within 15 seconds due to oxygen deprivation. Death would follow in about 90 seconds. Your body would swell, though it wouldn't explode like in some movies. This condition is called ebullism, and it's one of the most horrifying ways the Martian environment can kill you. Now you might be thinking, okay, but we can build habitats. We can create artificial environments. Absolutely true. But here's where it gets complicated. Creating a small, temporary habitat for a few astronauts is vastly different from building a self-sustaining civilization. Every single moment of every single day on Mars would require technology standing between you and instant death. There's no stepping outside for fresh air, no opening a window, no forgetting your helmet. One mistake, one equipment failure, one crack in your suit, and you're gone. Psychologically, This creates a pressure unlike anything humans have experienced in our entire history. Even Antarctica, Earth's harshest continent, offers air you can breathe and pressure your body can tolerate. Mars offers neither, and speaking of that thin atmosphere, let's talk about what it's made of. 95% carbon dioxide, about 2.8% nitrogen, 1.9% argon, only 0.15% oxygen, and that oxygen isn't in a form humans can breathe. It's molecular oxygen locked in carbon dioxide molecules. Earth's atmosphere, by comparison, is 78% nitrogen and 21% oxygen. This composition isn't arbitrary. It's the result of billions of years of geological and biological processes. Photosynthetic organisms, from ancient cyanobacteria to modern plants and algae, generated our oxygen-rich atmosphere over eons. Mars has no such life, no such processes. Creating a breathable atmosphere on Mars would require either shipping incomprehensible amounts of gas from Earth, which is economically impossible, or finding ways to break down Martian materials and release oxygen. Both scenarios require energy on scales that dwarf anything humanity has ever attempted. We're talking about industrial operations requiring hundreds of terawatts of power, sustained for centuries or millennia. For context, all of human civilization currently uses about 18 terawatts on average. If you're fascinated by Mars and want to observe it yourself from right here on Earth, I've created a complete guide for you. It's called Mars in 15 Minutes, the No Telescope Observation Guide. This ebook will show you exactly when and where to look, how to identify Mars among the stars, and what you're actually seeing when you gaze at that red dot in our night sky. You don't need expensive equipment, just your eyes, clear skies, and the knowledge inside this guide. It's perfect for anyone who wants to connect with the red planet personally before we dive deeper into the science of why it's so hostile to human life. The link is in the description below. Download it, head outside tonight, and see Mars for yourself. Now let's talk about something that doesn't get enough attention in popular discussions about Mars colonization: gravity, or rather, the lack of it. Mars has about 38% of Earth's gravitational pull. If you weigh 150 pounds on Earth, you'd weigh only 57 pounds on Mars. That might sound appealing, like you've suddenly become superhuman, able to jump higher and lift more, and initially, it would feel that way. Astronauts on Mars would indeed find physical tasks easier in some respects. But here's the problem. Your body isn't adapted to low gravity at all. Evolution spent hundreds of millions of years optimizing the human body for one specific gravitational environment, 1G, Earth normal. Every system in your body, from your cardiovascular system to your vestibular system to your musculoskeletal system, assumes that gravity. We've learned a lot about low gravity from astronauts on the International Space Station. 6-month missions in microgravity, which is even lower than Mars gravity, cause profound changes. Astronauts lose bone density at a rate of 1 to 2% per month. Their muscles atrophy, particularly in the legs and back, even with 2 hours of exercise daily. Their cardiovascular systems adapt to the reduced workload, with hearts becoming less efficient and blood pressure regulation suffering. Vision problems arise in many astronauts caused by increased intracranial pressure. Immune systems become compromised. The list goes on. Now, Mars isn't microgravity, it's 3/8 G, but we have exactly zero data on what that does to human bodies over months or years. We don't know if 3/8 G is enough to prevent the degradation seen in microgravity. We don't know if bone loss would continue indefinitely or plateau at some new equilibrium. We don't know if children could develop normally in Martian gravity, whether their bones would form properly, whether their hearts and lungs would be strong enough. These aren't minor questions. They're fundamental to the possibility of human settlement. Let's dig into one of the most terrifying aspects of Mars: radiation. This is where the red planet transforms from merely inhospitable to genuinely lethal over time. Right now, as you sit watching this video, you're protected by two invisible shields that you probably never think about. The first is Earth's magnetic field, generated deep within our planet's core. About 3,000 kilometers beneath your feet, the outer core of Earth consists of liquid iron and nickel, heated to temperatures exceeding 9,000 degrees Fahrenheit. This molten metal churns and flows, driven by the heat escaping from Earth's solid inner core and by the planet's rotation. This motion creates electric currents, and those currents generate Earth's magnetic field through a process called the geodynamo. The field extends tens of thousands of kilometers into space, creating a protective bubble called the magnetosphere. This isn't just an interesting geological curiosity. It's the reason life on Earth's surface is possible. The sun constantly ejects charged particles, protons and electrons, traveling at speeds between 250 and 400 miles per second. This solar wind would strip away our atmosphere and bombard the surface with deadly radiation if not for the magnetosphere. Earth's magnetic field deflects most of these particles, channeling them around the planet. Some particles do penetrate near the poles, creating the beautiful auroras we see in northern and southern latitudes. Those dancing lights are actually a visible sign of our magnetic shield at work, particles colliding with atmospheric gases at high altitudes. But the vast majority of solar wind particles never reach Earth's surface. They're swept around our planet and continue their journey through the solar system. Our second shield is the atmosphere itself. Even after the magnetosphere does its job, there's still radiation to contend with. Cosmic rays, high-energy particles from distant supernovas, and other violent cosmic events can penetrate the magnetic field. Earth's thick atmosphere, 10,000 kilograms of air pressing down on every square meter of surface, provides additional shielding. The atmosphere is equivalent to about 10 meters of water in terms of stopping power for radiation. By the time cosmic rays and solar particles make it through both the magnetosphere and the atmosphere, the radiation dose at Earth's surface is minimal. You receive about 0.3 to 0.6 millisieverts per year from cosmic sources, depending on your altitude and latitude. For comparison, a chest X-ray delivers about 0.1 millisieverts. Mars has neither of these protections. Let me explain why. About 4 billion years ago, early in Martian history, the planet likely had a global magnetic field similar to Earth's. We know this because NASA's MAVEN spacecraft, the Mars Atmosphere and Volatile Evolution mission, has detected patches of strongly magnetized crust in the southern highlands of Mars. These are like fossil remnants of an ancient magnetic field, locked into rocks when they solidified billions of years ago. But something happened. Mars's core cooled. The planet is much smaller than Earth, with only about 11% of our mass. Smaller planets have higher surface area to volume ratios, which means they radiate heat into space more efficiently. They cool faster. As Mars's interior cooled, the convection in its liquid outer core slowed and eventually stopped. Without that churning molten metal, the dynamo shut down. The magnetic field collapsed. The consequences were catastrophic for Mars as a potentially habitable world. Without a magnetic shield, the solar wind began directly interacting with the Martian atmosphere. Over hundreds of millions of years, charged particles from the Sun stripped away most of Mars's air. Scientists estimate that ancient Mars had an atmosphere thick enough to support liquid water on the surface, possibly several hundred millibars or even thicker. MAVEN's measurements show this stripping process is still happening today, though at a much slower rate since there's so little atmosphere left to lose. Mars currently loses about 100 grams of atmosphere to space every second. That might not sound like much, but over millions of years it adds up. For you, standing on Mars, this means you're exposed to the full fury of space radiation. NASA's Curiosity rover has been measuring radiation levels on Mars since it landed in Gale Crater in August of 2012. The rover carries an instrument called the Radiation Assessment Detector, built specifically to understand the radiation environment for future human missions. During Curiosity's 8.5-month journey to Mars, the instrument measured an average dose of 1.8 millisieverts per day. That's roughly equivalent to getting a whole-body CT scan every 5 days, continuously for the entire trip. On the Martian surface, the readings are somewhat better because the planet itself provides shielding from below, and the thin atmosphere provides a tiny amount of protection. Curiosity measured about 0.64 millisieverts per day on average, which translates to roughly 233 millisieverts per year. To put that in context, radiation workers on Earth, people who work with X-ray machines, nuclear reactors, or radioactive materials, are limited by law to 50 millisieverts per year. That's considered the upper boundary of acceptable occupational exposure. An astronaut on Mars would receive over 4 times that dose every single year, just from ambient radiation. And remember, that's the baseline. It gets worse during solar events. When the sun releases a coronal mass ejection, a massive eruption of plasma and magnetic field from its corona, Mars takes the full hit. These solar particle events can temporarily increase radiation levels on Mars by factors of 10 or more. On Earth, we're protected. On Mars, you'd need to scramble to a shielded shelter and hope you get there in time. Now let's talk about what this radiation actually does to you at the cellular level. Radiation comes in several forms, but the two most dangerous for Mars explorers are galactic cosmic rays and solar energetic particles. Solar particles are mostly protons, charged hydrogen nuclei, with energies typically between 10 and a few hundred million electron volts. They're dangerous, but spacecraft and habitat materials can provide some shielding. Galactic cosmic rays are far more sinister. These particles have been accelerated to tremendous energies, sometimes exceeding several billion electron volts, by the most violent events in the universe. Supernova explosions, colliding neutron stars, matter falling into black holes. These cosmic accelerators fling atomic nuclei into space at close to the speed of light. About 89% of cosmic rays are protons, 10% are helium nuclei, and 1% are heavier elements like carbon, oxygen, and iron. It's those heavy nuclei, traveling at relativistic speeds, that cause the most biological damage. When a high energy iron nucleus slams through your body, it doesn't just hit one cell. It creates a track of destruction through dozens of cells along its path. Unlike X-rays or gamma rays, which scatter their energy over a region, these heavy ions deposit enormous amounts of energy in a narrow column, completely destroying every cell they pass through. Your body's DNA repair mechanisms, which evolved to handle the low levels of radiation on Earth, are overwhelmed. The damage is too extensive, too complex. Some cells die immediately, others become damaged in ways that can lead to cancer years later. Still others may survive with genetic mutations that affect their function. The brain is particularly vulnerable. Research conducted at Brookhaven National Laboratory in New York, using particle beams to simulate cosmic ray exposure, has shown disturbing effects. Studies on mice exposed to radiation levels similar to what Mars astronauts would experience show significant cognitive impairment. The animals displayed problems with spatial memory, the kind you use to navigate and remember where things are. They showed increased anxiety behaviors. Examination of their brain tissue revealed inflammation and changes in the structure of neurons, particularly in the hippocampus, a region critical for memory formation. Research led by Charles Limoli at the University of California, Irvine, and published in the journal Scientific Reports in 2016, found that cosmic radiation exposure disrupts neural communication and reduces the complexity of neuronal dendrites, the branched structures that allow neurons to connect and form networks. Think about what this means for a Mars mission. You're spending 6 to 9 months traveling to Mars, already accumulating significant radiation exposure. Then you're on the surface for 18 months or more, the time required for Earth and Mars to realign for the return journey. Then another 6 to 9 months coming home. By the time you return to Earth, your total mission duration is roughly 30 months, or 2.5 years. During that time, your brain has been continuously bombarded by radiation that has measurably impaired cognitive function in every animal model tested. Your memory, your decision-making, your ability to learn new information, all potentially degraded. And you need these faculties to be sharp because you're operating complex life support systems in an environment where mistakes are fatal. Cancer risk is the other major concern. NASA has established career limits for astronaut radiation exposure based on limiting the lifetime risk of cancer death to no more than 3% above baseline. For a 40-year-old male astronaut, that translates to a career limit of about 400 millisieverts. For women and younger astronauts, the limits are lower because they have more years ahead of them for cancers to develop and because women appear to be more susceptible to certain radiation-induced cancers. A Mars mission, as currently envisioned, would expose astronauts to somewhere between 600 and 1,000 millisieverts, depending on solar activity during the mission and the specifics of the spacecraft shielding. That's beyond NASA's own safety guidelines. It essentially means an astronaut who goes to Mars is accepting a significantly elevated cancer risk as the price of the journey. You might be wondering whether we can shield against this radiation. After all, we've solved countless engineering challenges throughout human history. Surely we can figure out how to protect astronauts from radiation, right? This is where the physics becomes frustratingly uncooperative. Traditional radiation shielding works through a simple principle: put mass between you and the source. Lead aprons protect technicians during X-rays. Concrete walls surround nuclear reactors. Water tanks shield nuclear fuel rods. These approaches work well for lower energy radiation like X-rays and gamma rays, but cosmic rays are different. They're so energetic that conventional shielding can actually make the problem worse through a process called spallation or nuclear fragmentation. When an ultra-high energy cosmic ray particle smashes into a heavy nucleus, like those in lead or steel shielding, it breaks the nucleus apart. This creates a shower of secondary particles, neutrons, protons, lighter nuclei, and various subatomic debris, all traveling at high speeds. These secondary particles scatter in different directions, and many of them are still energetic enough to cause biological damage. In some cases, you end up with more radiation inside your shielded habitat than you would have outside. It's counterintuitive, but it's real physics. NASA and other space agencies have known about this problem for decades. The solution is to use lighter materials, particularly those rich in hydrogen. Hydrogen nuclei are single protons, the simplest atomic nucleus. When cosmic rays hit hydrogen, there's no complex nucleus to fragment. The interactions are cleaner, and the cosmic ray loses energy more efficiently through electromagnetic interactions rather than nuclear spallation. Materials like water, polyethylene plastics, and liquid hydrogen make excellent radiation shields. Some mission designs propose surrounding habitats with water tanks, which serve double duty as both radiation shielding and a vital resource. Other concepts involve using Martian soil itself. Regolith, the loose rocky material covering Mars's surface, is mostly silicon dioxide, iron oxide, and other relatively light compounds. Pile several meters of regolith on top of your habitat, and you significantly reduce radiation exposure. But here's the challenge. None of these solutions protect you everywhere. You can shield a small habitat, perhaps even bury it underground. But what about when you need to go outside? Mars exploration requires mobility, fieldwork, sample collection, equipment maintenance, and construction activities. Astronauts in bulky spacesuits have limited shielding. You can add water layers or polyethylene to spacesuits, but every kilogram of extra mass makes the suit harder to move in and requires more life support. There's a fundamental trade-off between protection and functionality. Some mission architectures propose using rovers as mobile shelters, small pressurized vehicles with better shielding than a spacesuit. You'd suit up only for brief periods to move between the rover and your destination. But this limits your flexibility and adds complexity. The transit to and from Mars presents an even thornier problem. Your spacecraft has mass constraints determined by rocket performance. Every kilogram of shielding is a kilogram not available for food, water, equipment, or scientific instruments. Mission planners are forced to make agonizing calculations about acceptable risk. Some concepts propose using consumables like water and food stores as makeshift shielding, arranging them around a small shelter area where the crew can retreat during solar particle events. Others suggest using spacecraft waste, storing bags of human feces and urine in the walls as radiation shielding. Yes, really, waste contains water and organic compounds, both hydrogen-rich. It's morbidly practical, but it illustrates how desperate the shielding challenge becomes. More ambitious concepts involve generating artificial magnetic fields around spacecraft or habitats. If we can't have a planetary magnetic field, perhaps we can create a miniature one. Researchers at the Rutherford Appleton Laboratory in the United Kingdom demonstrated in 2017 that superconducting magnets could theoretically deflect incoming radiation particles. The concept involves creating a magnetic bubble extending several meters around a spacecraft, strong enough to deflect charged particles. It's scientifically sound, but technologically daunting. Superconducting magnets require extreme cooling, usually to near absolute zero, which demands significant power and cryogenic systems. The magnets themselves are heavy. The power requirements are substantial, possibly requiring dedicated nuclear reactors. And you need redundancy because if the system fails during a solar storm, the crew is exposed. As of 2026, this technology remains in the conceptual and laboratory testing phase, nowhere near ready for actual space missions. Some researchers have proposed even more ambitious ideas for Mars itself. What if we could restart the Martian magnetic field? It sounds like science fiction, but scientists have seriously analyzed the concept. In 2017, Jim Green, then director of NASA's Planetary Science Division, presented a concept at the NASA Planetary Science Vision 2050 workshop. The idea involves placing a powerful magnetic dipole, essentially an artificial electromagnet, at the Mars L1 Lagrange point, the gravitational balance point between Mars and the Sun. This magnetic shield would deflect solar wind particles, reducing atmospheric stripping and potentially allowing the atmosphere to thicken over time through outgassing from the surface and subsurface. Computer simulations suggest such a shield could gradually increase Mars's atmospheric pressure and surface temperature over decades or centuries. It's a magnificent idea in terms of scale and ambition, but let's be realistic about the challenges. Creating a magnetic field strong enough to shield an entire planet, even a small one like Mars, requires a magnetic dipole with a field strength of several Teslas, sustained continuously. For reference, a typical hospital MRI machine operates at 1.5 to 3 Teslas, and that's only within a small chamber, sustained by superconducting magnets cooled with liquid helium. Scaling this up to planetary protection requires technology far beyond our current capabilities. The power requirements would be staggering. likely requiring multiple nuclear reactors launched to Mars orbit or the Lagrange point. The infrastructure needed to build, deploy, and maintain such a system would require decades of development and vast resources. It's theoretically possible according to physics, but practically impossible with anything resembling near-term technology. So where does this leave us with radiation? The uncomfortable truth is that we can reduce exposure but not eliminate it. Current technology allows us to cut radiation doses by factors of 2 to 5 through shielding, habitat design, and operational procedures. That's significant, but it still leaves Mars explorers receiving radiation doses far above terrestrial safety limits. We're essentially asking people to accept elevated cancer risk, potential cognitive impairment, possible cardiovascular effects, and other health consequences we don't fully understand. Some astronauts might accept these risks. Test pilots and explorers have always pushed boundaries. But asking people to settle on Mars, to raise families, to build a civilization, while accepting that their children will grow up bathed in radiation that increases their cancer risk by unknown amounts, that's a different ethical calculation altogether. And remember, radiation is just one challenge among many. Let's move on to another critical issue that gets less attention than it deserves: the soil. Martian regolith, the loose material covering the surface, is not soil in the Earth sense. Soil on Earth is a living system teeming with bacteria, fungi, nematodes, and countless other microorganisms. It's rich in organic compounds, the remains of dead plants and animals broken down over time. Martian regolith is sterile, lifeless, and potentially toxic. Missions to Mars, particularly the Phoenix lander in 2008 and more recent measurements by Curiosity, have detected significant amounts of perchlorates in Martian soil. Perchlorates are chlorine-containing compounds, salts of perchloric acid. They're present at concentrations of about 0.5 to 1% by weight, which is quite high. Perchlorates are toxic to humans. They interfere with iodine uptake by the thyroid gland, potentially causing hypothyroidism and developmental problems. Exposure can occur through ingestion, inhalation of dust, or even skin contact. On Mars, dust gets everywhere. It's fine, electrostatically charged and clingy. During the Apollo missions to the Moon, astronauts found lunar dust infiltrated their spacecraft, despite their best efforts to brush it off outside. The dust caused equipment problems, got into eyes and lungs, and proved nearly impossible to keep contained. Martian dust would pose similar challenges, with the added danger of perchlorate contamination. Growing food in Martian soil presents a major challenge because of these perchlorates. Plants can take up perchlorates from soil, concentrating them in edible tissues. You'd need to either remove perchlorates from the regolith before using it for agriculture, which requires washing with large amounts of water and disposing of the contaminated runoff, or you'd need to use imported soil or hydroponic systems that don't rely on Martian regolith at all. Both approaches require significant resources. Some research suggests certain bacteria could potentially break down perchlorates, offering a biological remediation approach, but this requires establishing and maintaining bacterial cultures, providing them with nutrients and energy, and ensuring they process the regolith effectively. It's another layer of complexity in an already monumentally complex endeavor. The iron oxide that gives Mars its distinctive red color presents other issues. Martian regolith is rich in oxidized iron compounds, essentially rust. These compounds can be reactive, particularly in the low humidity environment of Mars. Some research suggests Martian dust might trigger inflammatory responses in lungs similar to silicosis, the disease coal miners and stonecutters develop from inhaling fine mineral particles. The sharp, angular nature of Martian dust particles, never weathered by water and wind like Earth dust, makes them particularly dangerous to respiratory systems. During dust storms, which can envelop the entire planet for weeks at a time, the concentration of suspended particles in the atmosphere increases dramatically. Even small amounts infiltrating habitats could pose health risks over time. Speaking of dust storms, let's talk about Mars's weather, which is both more extreme and more alien than most people realize. The Martian atmosphere might be thin, but it's still capable of generating planet-wide phenomena that would make surviving on the surface incredibly challenging. Every Martian year, which lasts 687 Earth days, the planet experiences dust storm season. Most years bring regional storms that can cover areas the size of continents for weeks. But approximately every 3 to 4 Martian years, about once every 5 to 7 Earth years, conditions align to produce a global dust storm that engulfs the entire planet. We witnessed one of these global events in 2018. It began in late May of that year, and within weeks, dust obscured the entire Martian surface from orbital observation. The storm was so thick that NASA's Opportunity rover, which had been exploring Mars since January of 2004, lost solar power and fell silent. Mission controllers hoped Opportunity would weather the storm and reawaken when sunlight returned, but the rover never responded to subsequent communication attempts. After more than 14 years of extraordinary service and 45 kilometers of travel across the Martian surface, Opportunity was finally declared dead in February of 2019, claimed by the dust. These storms don't feature the hurricane-force winds you might imagine from movies like The Martian. The atmospheric pressure is so low that even wind speeds of 160 kilometers per hour, which sounds terrifying, produce forces equivalent to only about 15 to 20 kilometers per hour on Earth. A person could lean into a Martian dust storm wind and not be blown over, but the real danger isn't mechanical, it's the dust itself. During a global storm, the opacity of the atmosphere increases by factors of hundreds or thousands. Sunlight is blocked, temperatures change, and the static charge dust coats everything. For solar-powered equipment, it's potentially a death sentence. Opportunity's demise illustrates the vulnerability. For human explorers, global dust storms create cascading challenges. First, there's the power issue. Most Mars mission concepts rely heavily on solar panels because they're lighter and simpler than nuclear reactors. But when dust blocks 99% of sunlight for weeks or months, solar power becomes useless. You need backup systems, likely nuclear fission reactors, which require complex safety systems and shielding. NASA's Curiosity and Perseverance rovers use radioisotope thermoelectric generators, devices that convert heat from radioactive decay into electricity. They're reliable regardless of dust storms, but they're expensive, heavy, and politically complicated to launch due to the radioactive materials involved. Second, thermal control becomes difficult. Mars's thin atmosphere means the planet cools rapidly at night under normal conditions, but during dust storms, the suspended particles trap some infrared radiation, acting like a weak greenhouse effect. Surface temperatures can actually increase slightly during daytime storms, while nighttime temperatures don't drop as severely. This might sound beneficial, but it disrupts thermal management systems designed for predictable temperature cycles. Equipment can overheat or fail to cool properly. Habitats designed with specific thermal assumptions might struggle to maintain stable interior temperatures. Third, there's the issue of visibility and mobility. During intense storms, you can't see more than a few meters. Navigation becomes nearly impossible without instruments. If you're outside when a storm hits, even with a good spacesuit radio, you could easily become disoriented and lost. On Earth, if you get lost in a snowstorm, at least you can breathe while you figure out what to do. On Mars, your suit has a finite air supply, perhaps 4 to 8 hours depending on the system. Get lost, and you're on a clock counting down to suffocation. The temperature extremes I mentioned earlier aren't just uncomfortable, they create serious engineering challenges for equipment and materials. Metals become brittle at low temperatures, seals and gaskets can fail, lubricants freeze, electronics can malfunction. Every piece of equipment designed for Mars needs to function across a temperature range of roughly 340 degrees Fahrenheit, from -284 to 59 degrees. For comparison, most commercial electronics are rated for maybe 180 degrees of range, from -40 to 140 Fahrenheit. Space-rated electronics can handle wider ranges, but they're expensive, heavy, and limited in capability compared to consumer technology. Water management on Mars is perhaps the most critical and complex challenge for any long-term human presence. Water is essential for life, obviously, but it's also needed for agriculture, hygiene, radiation shielding, oxygen production through electrolysis, and hydrogen fuel production. An average human needs about 2 liters of drinking water per day, but total water use, including hygiene, food preparation, and sanitation, can easily exceed 15 liters per person per day, even with aggressive recycling. A crew of 6 for an 18-month surface stay would need at least 160,000 liters without recycling, or about 16,000 liters with 90% efficient recycling systems. Does Mars have water? Absolutely. The planet holds vast amounts of water ice, primarily in the polar ice caps, but also in subsurface deposits at various latitudes. NASA's Mars Reconnaissance Orbiter, using ground-penetrating radar, has mapped extensive ice deposits buried under Martian soil. The Phoenix lander in 2008 excavated water ice just centimeters below the surface at its landing site in the northern Arctic region. More recently, in 2018, radar data revealed a possible liquid water lake beneath the southern polar ice cap, though this finding remains controversial and debated among scientists. But here's the problem. Accessing and processing this water requires significant energy and infrastructure. If you land in a region with subsurface ice, you need to excavate regolith, heat it to sublimate or melt the ice, capture the resulting water vapor or liquid, purify it to remove perchlorates and other contaminants, and then store it. Each step requires equipment, power, and time. The ice isn't pure. It's mixed with soil and rocks. Heating regolith to release water requires reaching temperatures of at least 150 to 200 degrees Celsius to drive off water efficiently. That takes considerable energy, especially when you're heating tons of frozen dirt. Some regions of Mars have more accessible water than others. Higher latitudes, closer to the poles, have ice nearer the surface and in higher concentrations, but these regions are also colder and receive less sunlight, making solar power less effective. Equatorial regions are warmer and sunnier, but have water ice buried much deeper, if at all, or locked in hydrated minerals that require even more energy to process. Every landing site selection becomes a complex optimization problem, balancing water access, solar power availability, temperature extremes, landing safety, and scientific interest. Even if you solve the extraction problem, water on Mars behaves strangely because of the low atmospheric pressure. At 6.1 millibars, you're right at the triple point of water. Below this pressure, liquid water cannot exist stably. Water ice sublimates directly to vapor without melting, or if you do create liquid water, it rapidly boils and freezes simultaneously, a bizarre process where it essentially tears itself apart. This makes working with water on the Martian surface extremely difficult. Any plumbing, any open containers, any spills, they don't behave the way your Earth-trained intuition expects. Pressurized habitats can maintain conditions where liquid water is stable, but the moment you have a pressure breach, all your water is in danger. Imagine a scenario where a small meteorite punctures your water tank. On Earth, water would leak out as a liquid, and you could potentially seal the breach. On Mars, the water explosively boils and freezes, creating ice crystals and vapor that escape into the thin atmosphere. You lose your water almost instantly, and the escaping vapor can damage nearby equipment or obscure vision. It's one more way the Martian environment punishes mistakes. Agriculture on Mars faces obstacles beyond just perchlorate-contaminated soil. Plants evolved in Earth's environment, which includes not just the right temperatures and water, but also the correct atmospheric composition and pressure. Mars's atmosphere is 95% carbon dioxide, which plants use for photosynthesis, so that's actually helpful. But the pressure is the killer. At 6 millibars, water evaporates from plant tissues faster than the plant can replace it, even in humid conditions. You essentially need to grow plants in pressurized greenhouses, which brings us back to the engineering challenges of maintaining large pressurized structures. NASA and other organizations have conducted numerous studies on growing food in Martian conditions. Researchers at Wageningen University in the Netherlands have run experiments since 2013 growing crops in simulated Martian soil. They've successfully grown tomatoes, peas, rye, radishes, and other vegetables in regolith simulants after adding organic matter and removing perchlorates. The results are encouraging from a purely agricultural standpoint, but they underscore how much intervention is required. You can't just plant seeds in Martian dirt and expect food. You need to create soil, a living system, which requires importing or producing organic material, managing microbial communities, controlling temperature and humidity precisely, providing supplemental lighting during dust storms, and maintaining all of this within pressurized, heated structures. The energy budget for a Mars colony becomes staggering when you add up all the requirements. You need power for life support, recycling air and water. You need power for heating, because remember, outside temperatures average -80 Fahrenheit. You need power for lighting, both for habitats and for agriculture. You need power for water extraction and purification. You need power for communications with Earth, manufacturing, and scientific research. Some estimates suggest a small crew of 6 to 10 people would require continuous power in the range of 40 to 100 kilowatts, depending on the efficiency of their systems and the extent of their activities. For comparison, the average American home uses about 1 to 2 kilowatts on average throughout the day. Where does this power come from? Solar panels are the obvious choice, and they work reasonably well on Mars. The planet receives about 44% as much sunlight as Earth on average, since it's farther from the Sun. Mars's thin atmosphere means less light is absorbed or scattered, so panels can be more efficient than you'd expect. But dust accumulation is a constant problem, reducing panel efficiency by percentages each week until they're cleaned. The rovers have occasionally benefited from cleaning events, where wind happens to blow dust off the panels, but you can't rely on that. Some human missions would require crew members to regularly go outside and clean solar arrays, adding to workload and radiation exposure. Nuclear power is the more reliable alternative. A fission reactor doesn't care about dust storms, day-night cycles, or seasonal variations. It produces steady power for years or decades. NASA has developed the kilopower system, a small fission reactor designed to produce 1 to 10 kilowatts of electrical power continuously for at least 10 years. 4 of these reactors could provide 40 kilowatts, enough for a small base. The technology is solid, tested, and ready for deployment. But nuclear systems come with their own complications. First, there's the political and regulatory challenge of launching nuclear materials into space. The kilopower reactor uses highly enriched uranium, the same material used in nuclear weapons, though in much smaller quantities. International treaties and domestic laws regulate the production, transport, and use of such materials. Public opposition to launching nuclear reactors based on fears of launch accidents spreading radioactive contamination has historically been intense. NASA has launched nuclear power systems before, most notably the radioisotope generators on Voyager, Cassini, Curiosity, and Perseverance, but these missions required extensive environmental reviews and risk assessments. Scaling up to larger fission reactors for human missions would face even greater scrutiny. Second, nuclear reactors produce heat that must be dissipated. On Earth, we use water or air cooling. On Mars, there's no water to spare, and the thin atmosphere is a terrible heat conductor. Reactors would need large radiator panels to reject waste heat into space via thermal radiation. These radiators add mass and complexity. They're also vulnerable to damage from dust accumulation, which reduces their emissivity, or from micrometeorite impacts. The colder the Martian environment, the less efficiently heat radiates away, which seems counterintuitive, but thermal radiation follows the Stefan Boltzmann law. Depending on the temperature difference between the radiator and the environment, the colder Mars gets at night, the harder it is to dump heat. Third, nuclear systems require shielding and separation from living areas. You don't want your crew sleeping next to an operating fission reactor. The reactor needs to be positioned at least several hundred meters from habitats, with power cables running underground or along the surface. This creates infrastructure sprawl and vulnerability. A cable break during a dust storm or equipment failure could cut power to critical life support systems. Let's talk about isolation and communication, psychological factors that often get overlooked in technical discussions but are absolutely critical for long-duration missions. Mars is far away, not just in kilometers, but in terms of communication time. Radio waves, traveling at the speed of light, take between 3 and 22 minutes to reach Mars from Earth, depending on where the planets are in their orbits. This means round-trip communication delays range from 6 to 44 minutes. Imagine having an emergency. Something breaks, life support is failing, and you need help from mission control. You describe the problem, transmit your message, and then wait. 6 minutes pass at best, 22 at worst, before your message reaches Earth. The engineers there analyze your situation, formulate a response, and send it back. As another 6 to 22 minutes, at minimum 12 minutes pass before you receive a reply. At maximum, you're waiting 44 minutes. If the problem requires back and forth troubleshooting, multiple exchanges, you could be dealing with hours of communication delay while your air runs out or your water systems fail. This communication lag fundamentally changes how Mars missions must operate compared to every other human spaceflight in history. The International Space Station orbits 400 kilometers above Earth. Communication is essentially instantaneous, a fraction of a second delay. If something goes wrong, mission control can provide real-time guidance. Astronauts and engineers work together moment by moment to solve problems. The Apollo missions to the Moon had roughly a 3-second round-trip delay, noticeable but still allowing for conversation. Mars is different. Mars crews must be far more autonomous. They need to diagnose and solve problems themselves, with mission control providing advice asynchronously, more like email than a phone call. This requires a different type of crew selection and training. You need people who can function independently, make critical decisions under pressure without external guidance, and maintain psychological stability in isolation. The Antarctic research stations provide the closest terrestrial analog. Crews winter over for months in extreme isolation, unable to leave, with limited communication and supply chains. Psychological studies from these stations show increased rates of depression, interpersonal conflict, and cognitive impairment, even in groups of highly trained, motivated individuals who volunteered for the experience. Mars will be worse. longer duration, smaller crews, more danger, more confinement, and much greater consequences for failure. The psychological strain of confinement in small spaces, breathing recycled air, eating monotonous food, unable to go outside without extensive preparation, surrounded by a landscape that wants to kill you, cut off from Earth by tens of millions of kilometers, this grinds people down. NASA has run isolation experiments, most notably the High Seas missions in Hawaii, where crews lived in Mars analog habitats for periods up to a year. Participants reported significant psychological challenges, despite knowing they could abort the mission at any time if they truly needed to. On actual Mars, there is no abort, there is no rescue. If you have a psychological breakdown, your crew has to manage it themselves. The lack of privacy in small habitats creates constant low-level stress. Early Mars missions might feature habitats with only 50 to 100 cubic meters of pressurized volume per person, roughly the size of a small bedroom. You eat, sleep, work, and live in this space for months. You hear every sound from your crewmates. You smell them. You see them constantly. Research on submarine crews and Antarctic stations shows that minor irritations, someone's eating habits, their laugh, their mannerisms, become sources of intense frustration over time. On a submarine, tours last a few months before the crew rotates out. Antarctic winterovers last 6 to 12 months. Mars missions would be 30 months or more. The cumulative psychological load is enormous. Then there's the Earth separation itself. You look up, and Earth is a bright star, sometimes a tiny blue dot through a telescope, but fundamentally distant and unreachable. Everyone you've ever known except your handful of crewmates is on that dot. You watch videos from home, but they're hours or days old by the time you receive them. You miss births, deaths, weddings, and emergencies. Your family experiences a crisis, and you hear about it 20 minutes after the fact, unable to help or comfort them. This emotional distance can be agonizing, even for the most stoic individuals. Some people might think the solution is to send larger crews, but that brings different problems. More people means more complex social dynamics, more potential for conflict, and higher resource requirements. Small crews of 4 to 6 people create intense interdependence. Everyone relies on everyone else, which can build cohesion but also amplify conflicts. Larger crews of 10 to 20 people allow for more social flexibility, subgroups and friendships, but require vastly more habitat space, life support capacity, food, water, and power. There's no magic number. Every crew size involves trade-offs. The gravity issue extends beyond just bone and muscle loss. Mars has 38% of Earth's gravity, which is significantly more than the Moon's 16%, but still far less than what our bodies evolved for. We don't yet know the long-term health effects of Martian gravity because no human has ever experienced it. All our data comes from either microgravity, essentially 0G on the ISS, or 1/6 gravity during brief Apollo moon walks. The question of whether Mars gravity is sufficient to prevent the bone loss, muscle atrophy, cardiovascular deconditioning, and immune system impairment seen in 0G is unresolved. Some scientists are optimistic, arguing that partial gravity is fundamentally different from 0G, and that Martian gravity might be enough to maintain most physiological functions. Others are pessimistic, pointing out that even if Mars gravity slows degeneration compared to 0G, 18 months of reduced gravity loading might still cause significant irreversible damage. We simply don't know. Ideally, we'd test this with centrifuge studies on the ISS, creating artificial gravity at Mars levels to see how organisms respond. But building a large centrifuge in space is expensive and complex, and it hasn't been a funding priority. Here's a particularly concerning scenario. Imagine you're part of the first Mars landing crew. You spend 7 months getting there in 0G. Your bones are already weakening, your muscles atrophying despite exercise countermeasures. You land on Mars and spend 18 months in 38% gravity. Your body partially adapts, but it's still not full Earth loading. Then you spend another 7 months in 0G coming home. By the time you land back on Earth, you've experienced 32 months of reduced gravity. Studies of astronauts returning from 6-month ISS missions show they need weeks to months of rehabilitation to walk normally again. Some have fainted upon standing due to orthostatic intolerance, where blood pools in their legs instead of circulating properly. Bone density losses take years to recover, if they fully recover at all. Now multiply those effects by a factor of 5 or 6 for mission duration. Will Mars astronauts be able to walk when they return to Earth? Will they suffer fractures during re-entry and landing as weakened bones break under suddenly restored Earth gravity? Will their hearts, deconditioned by months of reduced cardiovascular demand, be able to pump blood effectively against Earth's gravity? These aren't hypothetical concerns. They're real physiological risks that current medical science cannot adequately mitigate. Some mission architectures propose one-way trips, acknowledging that return might be medically inadvisable or technically impossible with early technology. Crews would go to Mars, knowing they'll spend the rest of their lives there, however long that might be. This raises profound ethical questions. Are we asking people to commit suicide slowly by moving to an environment that will eventually kill them through radiation, accidents, or system failures? Or is it a legitimate choice for people to pioneer a new world, accepting the risks as explorers always have? The concept of in-situ resource utilization is central to almost every Mars colonization plan. The basic idea is simple. Instead of bringing everything from Earth, use local Martian resources to produce water, oxygen, fuel, and building materials. This dramatically reduces the mass you need to launch from Earth, making missions more feasible and affordable. But the devil, as always, is in the details, and those details reveal just how challenging ISRU actually is in practice. Let's start with oxygen production, since humans need it rather urgently. The Martian atmosphere is 95% carbon dioxide. Through a process called solid oxide electrolysis, you can break CO2 molecules apart using electricity, producing oxygen gas and carbon monoxide. NASA's MOXIE experiment, Mars Oxygen In Situ Resource Utilization Experiment, aboard the Perseverance rover, has been demonstrating this technology since 2021. As of 2026, MOXIE has successfully produced oxygen multiple times, proving the concept works on Mars. But there's a vast difference between a small experimental device producing a few grams of oxygen per hour and a system capable of supporting human life. A single person at rest consumes about 840 grams of oxygen per day, roughly 35 grams per hour. During physical activity, that rate can double or triple. A crew of 6 needs at least 5 kilograms of oxygen per day at minimum, likely 10 or more accounting for activity and system inefficiencies. To provide this, you'd need oxygen production systems running continuously, consuming significant electrical power. The MOXIE unit uses about 300 watts to produce about 6 grams of oxygen per hour under optimal conditions. Scale that up to meet crew needs, and you're looking at kilowatts of continuous power just for oxygen production, not counting the power needed to compress and store the oxygen or to operate backup systems. Water production from Martian ice requires even more energy. You need to excavate regolith, transport it to a processing facility, heat it to release water, condense the vapor, purify the water to remove perchlorates and other contaminants, and then store it. Let's do some rough math. Heating 1 kilogram of ice from -100 degrees Celsius, a typical subsurface temperature at mid-latitudes, to 0 degrees Celsius requires about 200 kilojoules of energy. Melting it takes another 334 kilojoules. That's 534 kilojoules per kilogram, or 0.15 kilowatt-hours. If your regolith is only 10% water by weight, you need to process 10 kilograms of regolith to get 1 kilogram of water, requiring 1.5 kilowatt-hours of thermal energy. A crew of 6 using 15 liters of water per person per day, 90 liters total, that's 90 kilograms of water, requiring 135 kilowatt-hours of thermal energy per day if processing 10% ice-rich regolith. Converting this from electricity, even with perfect efficiency, which you never have, means 20 to 30 kilowatts of continuous power just for water production. These numbers add up fast. Oxygen production, 10 kilowatts. Water production, 20 to 30 kilowatts. Habitat heating, 10 to 20 kilowatts, depending on insulation and outside temperature. Life support systems, 5 kilowatts. Agriculture lighting and climate control, 20 to 40 kilowatts. Communications, manufacturing, research, and other activities, 10 to 20 kilowatts. You're easily looking at 75 to 100 kilowatts of continuous power demand for a small base of 6 people. That's a substantial power plant by space exploration standards. Fuel production is another ISRU goal. The most commonly proposed approach is the Sabatier reaction, which combines carbon dioxide from the atmosphere with hydrogen to produce methane and water. Methane is a good rocket fuel, and if you electrolyze the water byproduct, you get oxygen to use as the oxidizer. This is attractive because it means you could refuel your return spacecraft using Martian resources, avoiding the need to bring all that propellant from Earth. SpaceX's Starship design explicitly depends on this, planning to use methane oxygen engines that can be refueled on Mars. But again, the devil is in the details. The Sabatier reaction requires hydrogen, which Mars doesn't have in large quantities. You can extract hydrogen from water by electrolysis, but that requires water, which requires mining ice, which requires energy. It's circular. You need energy to get water, water to get hydrogen, hydrogen to make fuel, and fuel to leave Mars. Each step has inefficiencies. Real-world chemical plants achieve perhaps 70 to 80% efficiency in these processes. That means you need to input significantly more resources than the theoretical minimum. Let's trace through the fuel production chain. You want to produce 1 kilogram of methane. The Sabatier reaction is CO2 plus 4H2 CH2A plus 2 CH2O. The stoichiometry tells us you need 4 kilograms of hydrogen for every 16 kilograms of methane produced, accounting for molecular weights. That's a 1/4 kilogram of hydrogen per kilogram of methane. To get that hydrogen, you electrolyze water, 2H2O, 2H2 plus O2. You need 2.25 kilograms of water to produce a 1/4 kilogram of hydrogen. That water came from mining and processing 22.5 kilograms of 10% ice regolith. The energy inputs accumulate at each stage: excavation, transportation, heating, electrolysis, chemical reaction, purification, and storage. A fully fueled Starship for return to Earth requires roughly 1,000 tons of propellant. Assuming a 6:1 oxygen to methane ratio, that's about 140 tons of methane and 860 tons of oxygen. Producing this amount of fuel on Mars would require processing millions of kilograms of regolith, millions of cubic meters of atmosphere, and consuming gigawatt hours of energy over months or years. The infrastructure needed is not a small laboratory device, but a full industrial facility with excavation equipment, storage tanks, compressors, chemical reactors, and power plants. This is heavy industry, not exploration science. Building infrastructure on Mars faces unique construction challenges. Materials brought from Earth are expensive, costing thousands to tens of thousands of dollars per kilogram to deliver. Using local materials is essential, but Martian regolith isn't soil or sand or gravel in the familiar sense. It's extremely fine, almost like powder, with particles ranging from silt to clay size, much finer than beach sand. It's also dry, containing no water to provide cohesion. It's been compared to flour or powdered cement. Building with this material requires binding agents. Some concepts propose sintering regolith using concentrated solar energy or microwaves to melt the particles together, essentially creating crude bricks or building blocks. Others suggest mixing regolith with polymers brought from Earth to create a sort of concrete. Still others propose 3D printing structures using regolith-based inks. All of these have been demonstrated in laboratory conditions using Martian regolith simulants, but scaling them up to construct pressurized habitats large enough for humans, with walls thick enough to provide radiation shielding and pressure containment, that's a monumental engineering challenge. A pressurized habitat on Mars needs to withstand an internal pressure of about 1 atmosphere, 100 kilopascals, while the outside is essentially vacuum. That creates an outward force of 10 tons per square meter of wall area. A modest habitat with 100 square meters of floor space and 3-meter-high walls has about 280 square meters of wall and ceiling area, experiencing outward forces totaling 2,800 tons. That's the weight of about 400 elephants pushing outward constantly. Your structure needs to be incredibly strong, which means thick walls, robust supports, and reliable seals. Any weakness, any crack results in catastrophic decompression. Traditional construction methods don't work in spacesuits. Astronauts wearing bulky pressurized suits have limited dexterity, grip strength, and endurance. Construction tasks that take minutes on Earth take hours on Mars. Welding and bonding materials behave differently in low pressure and extreme temperatures. Adhesives designed for Earth conditions might not cure properly. Metals become brittle, seals fail. Every construction technique needs to be tested and verified for Martian conditions, and that testing is expensive and time-consuming. The alternative is to prefabricate habitats on Earth and land them intact on Mars. This is the approach for early missions. NASA's Mars habitat concepts are essentially large pressurized cans launched from Earth, landed on Mars, and perhaps covered with regolith for radiation shielding. SpaceX's Starship is intended to serve double duty as both transportation and habitat, at least initially. But prefabricated structures have size limits determined by launch vehicle capacity and landing system capabilities. You can't build a sprawling complex this way. To grow beyond a small outpost requires construction, and construction on Mars is painfully difficult. Let's talk about something that rarely gets discussed: the smell. Closed-loop life support systems recycle air and water, but they're not perfect. Trace contaminants accumulate over time. On the ISS, astronauts report that the station has a distinctive metallic, antiseptic smell, with occasional whiffs of body odor, off-gassing plastics and equipment. The ISS has resupply missions every few months, bringing fresh filters and scrubbers. A Mars base would have resupply perhaps every 2 years during favorable launch windows. Between resupply missions, you're managing air quality with what you have. Humans produce more than just carbon dioxide when they exhale. We release moisture, obviously, but also volatile organic compounds, trace gases from digestion and metabolism, methane, ammonia, acetone, and dozens of other compounds in tiny quantities. Normally, these are diluted and dispersed in Earth's vast atmosphere. In a sealed habitat, they accumulate. Air scrubbers remove some contaminants, but not all. Over months, the air quality degrades subtly. It's not immediately dangerous, but it affects comfort and potentially health. Then there's the waste. Human waste management in space is complex and unglamorous, but absolutely critical. On the ISS, solid waste is collected and stored in sealed containers, then loaded into cargo spacecraft that burn up on re-entry, incinerating the waste in the atmosphere. Urine is processed through the water recovery system, purifying it back into drinkable water. The system works well enough for 6-month missions with regular resupply, but it requires maintenance, spare parts, and occasionally fails in ways that are disgusting and difficult to fix in microgravity. On Mars, you can't just burn up waste in the atmosphere. You need to manage it sustainably. Human waste contains water, nitrogen, phosphorus, and organic matter that are actually valuable resources. The ideal system would recycle everything, processing waste into water, fertilizer for agriculture, and perhaps even energy through anaerobic digestion. But building and maintaining such a system requires biological and chemical engineering expertise, energy, and infrastructure. Early missions will likely use simpler systems, storing or burying waste, but long-term sustainability demands closed-loop recycling. Composting human waste to create fertilizer for agriculture sounds elegant in theory. In practice, human waste contains pathogens, bacteria, viruses, and parasites that are dangerous if not properly treated. Composting requires time, temperature control, and careful management to kill pathogens while preserving nutrients. You need space for composting bins or reactors, time for the process to complete, which can take months for proper pathogen elimination, and monitoring to ensure safety. In a confined habitat where a disease outbreak could be catastrophic, you can't afford to get waste management wrong. The monotony of food deserves special mention. Early Mars crews will eat primarily freeze-dried or thermostabilized foods brought from Earth, similar to what astronauts eat on the ISS. These foods are nutritionally adequate but become psychologically wearing over time. Astronauts on long missions report intense cravings for fresh foods, fruits, vegetables, anything with texture and flavor that isn't rehydrated or shelf-stable. The psychological boost from food variety and quality is significant, affecting morale, motivation, and mental health. Growing fresh food on Mars helps but doesn't solve the problem completely. The crops you can grow in a Martian greenhouse are limited by energy, space, and time. Fast-growing vegetables like lettuce, radishes, and herbs are feasible. Grains like wheat or rice require more space and time. Fruits take even longer. Protein is particularly challenging. Growing protein-rich crops like beans and peas is possible, but they require more resources than leafy greens. Raising animals for meat is probably impractical for early missions due to the resource demands. Animals need food, water, space, and waste management. Insect farming for protein has been proposed. Insects like crickets or mealworms are efficient protein converters, but cultural acceptance is an issue for many people. Realistically, Mars crews will eat a predominantly plant-based diet with limited variety, supplemented by packaged proteins and fats from Earth. This is healthy from a nutritional standpoint, but can be depressing from a psychological one. Imagine eating mostly the same dozen or so ingredients, combined in different ways, for years. No chocolate unless you brought it from Earth and it's carefully rationed. No coffee unless resupply brings it. No cheese, no fresh meat, no seafood, no tropical fruits. None of the thousands of food varieties that Earth offers. Food becomes functional rather than pleasurable, and that's a subtle but persistent psychological burden. Alcohol is another interesting consideration. Historically, isolated groups, sailors, polar explorers, remote workers, have used alcohol for recreation and morale. Some Antarctic stations have bars where crew members socialize over drinks. But alcohol on Mars is complicated. Producing it locally requires agricultural resources, grain or fruit for fermentation, that might be better used for nutrition. Bringing it from Earth means dedicating cargo capacity to what's essentially recreational drugs rather than critical supplies. And alcohol affects judgment and coordination, which is dangerous in an environment where mistakes kill people. Some mission planners argue for allowing limited alcohol rations for psychological health. Others argue it's an unnecessary risk. There's no consensus, Medical care on Mars is perhaps the most terrifying aspect of the isolation. On Earth, if you have a medical emergency, you can usually reach advanced care within hours. In remote locations, you might wait a day or two for evacuation, but rescue is possible. On Mars, there is no rescue, there is no evacuation. Whatever medical capabilities you have with you are all you have. If someone gets sick or injured beyond your ability to treat, they die, and the crew has to deal with that. Mars missions will carry trained medics, probably crew members with physician or surgeon qualifications, plus specialized training for space medicine and remote care. They'll have medical supplies, diagnostic equipment, and pharmaceuticals for common illnesses and injuries. But the scope of what they can handle is limited by equipment, expertise, and the environment. Performing surgery in Martian gravity with limited sterile facilities is vastly more difficult than in a well-equipped Earth hospital. After everything you've just learned so far, you'd think we'd give up on Mars entirely, but we won't, and neither will you. That's the paradox of Mars. Deadly, hostile, maybe unconquerable, yet we can't look away. If you would like to see Mars for yourself, I've created an ebook called Mars in 15 Minutes, the No Telescope Observation Guide. It'll show you how to find Mars with just your naked eye. Download it on the link in the description. Even if we can't live there, we can still look up and wonder, see the planet that might end us, but will never stop calling to us. Consider appendicitis, a common medical emergency. On Earth, treatment is straightforward. Antibiotics if caught early, or surgical removal of the appendix if necessary. The surgery is routine, performed millions of times per year with very low risk. On Mars, you don't have an operating room with a full surgical team, anesthesiologists, sterilization equipment, and backup systems. You have a makeshift medical area, maybe one surgeon, limited anesthesia and pain management options, and no emergency backup if something goes wrong. Can you perform an appendectomy successfully under these conditions? Maybe, if everything goes right. But the risk of complications, infection, bleeding, anesthesia problems is much higher. Now consider more serious conditions. What if someone develops cancer? Radiation exposure on Mars increases cancer risk, so this isn't hypothetical. Cancer treatment on Earth involves sophisticated imaging, surgery, chemotherapy, radiation therapy, and long-term monitoring. None of this is available on Mars. The best you can do is provide palliative care, pain management, and comfort while the person dies. That's a devastating reality for both the patient and the crew, who must watch someone deteriorate over weeks or months with no ability to save them. Traumatic injuries from accidents are another concern. Suppose someone falls from a height in Martian gravity and breaks their spine. On Earth, you'd stabilize them, transport them to a trauma center, perform imaging to assess damage, potentially do surgery to stabilize vertebrae, and provide rehabilitation. On Mars, you stabilize them with what you have and hope. If the spinal cord is severed, they're paraplegic or quadriplegic for life, requiring constant care from the crew. If internal bleeding is occurring, you might not have the imaging capability to detect it until it's too late. Mental health crises are particularly challenging because they can't be treated with just medications and procedures. Someone experiencing severe depression, psychosis, or suicidal ideation needs therapy, possibly psychiatric medication, and sometimes removal from the stressful environment. On Mars, you can't remove them from the environment. They're stuck there, and so is everyone else. The crew has to manage the situation with psychological training, medications if available, and support, but options are limited. In extreme cases, a mentally unstable crew member could endanger the entire mission, and the hard reality is that restraint or sedation might become necessary, raising profound ethical questions. Death on Mars has to be addressed in mission planning, even though it's uncomfortable. What do you do with a body? On Earth, we have burial, cremation, or other cultural practices. On Mars, burial in the regolith is possible, but shallow graves risk exposure by future excavation or wind erosion. Deep burial requires excavation equipment and energy. Cremation requires significant energy to reach the necessary temperatures and produces emissions that need to be managed. Some have suggested simply leaving bodies in sealed containers on the surface, preserved by the cold and dry conditions, essentially mummification. Others suggest processing bodies similarly to other organic waste, which is practical but culturally disturbing for many people. There's also the question of how the crew psychologically processes a death. On Earth, when someone dies, we have rituals, funerals, grieving processes, and the ability to separate from the deceased. On Mars, the body remains present. Your crew member dies, and their body is 20 meters away in a sealed container, or buried 100 meters from your habitat. Every time you go outside, you pass their grave. The psychological impact of living with death in such proximity, in such isolation, is profound. Let's shift to discussing the return journey, assuming the mission is round trip. After spending 18 months on Mars, your crew boards the return vehicle. If they've been producing fuel using ISRU, that process needs to have worked flawlessly for months. If there were any problems, delays in fuel production, equipment failures, contamination, the return vehicle might not be fully fueled. At that point, you have impossible decisions. Do you wait another 2 years for the next launch window while supplies dwindle? Do you launch with partial fuel knowing you won't reach Earth, but might get close enough for a rescue mission, if anyone can mount one? Do you accept that you're staying on Mars permanently? Assuming the fuel production succeeded, you launch from Mars. This requires a launch system that's been sitting on the Martian surface for over a year, exposed to dust, temperature cycles, and cosmic radiation. Equipment degrades, seals crack, electronics fail. You perform pre-flight checks, but you don't have a full ground support infrastructure. You're essentially launching on hope and engineering redundancy. The Martian gravity is lower, so reaching orbit requires less delta V than launching from Earth, about 6 kilometers per second compared to 9.5. That's helpful, but it's still a violent high-energy event with no room for error. Once in orbit, you rendezvous with a transfer vehicle if your architecture uses separate landers and cruise ships, or you simply burn for Earth if your vehicle serves both roles. Now begins another 7 months of zero-gravity cruise. Your crew is already weakened from 18 months in Martian gravity. Their bones are brittle, muscles atrophied, cardiovascular systems deconditioned. 7 more months of zero-G deteriorates them further. By the time they approach Earth, they've been away from full gravity for 32 months. They're physically wrecked. Re-entry into Earth's atmosphere is among the most dangerous phases of any space mission. You're hitting the atmosphere at 11 kilometers per second, Earth's escape velocity, after a transfer from Mars. The kinetic energy must be dissipated as heat, creating a plasma sheath around the spacecraft that reaches thousands of degrees. Your heat shield must work perfectly. If there's any damage from the long journey, micrometeorite impacts, material degradation, structural fatigue, the spacecraft could burn up.